Hi students, in the last class we were discussing about the black body radiation, and Rayleigh and Jean they made a formula using the classical approach to get the energy density, and his relation that gave you a discrepancy with the observed spectra of the radiation, and that we called as the ultraviolet catastrophe. And after that, Planck he formulated by using the concept of the quanta of photons, and he got the relation for the energy density, and it was well fitted for the observed spectra of black body radiation. Okay, and today we are going to get the Stefan-Boltzann's law. Actually, that give you the radiation R per unit area per unit second. So we will start with the Planck's radiation formula, and we will integrate it, and we will get the Stefan-Boltzann's law. Okay. So first we will Stefan-Boltzann. So this we want to discuss. So I told we will just first we will write the Planck's radiation formula. So the Planck's radiation formula, what was it? U nu d nu is equal to 8 from CQ nu cube d nu divided by e raised to h nu by kBt minus 1. So this was the Planck's radiation formula. Now what you are going to do? You are going to get the total energy density U of the radiation in a cavity. So in order to get the total energy density, what you have to do? You have to integrate it for the whole frequency that is available in the cavity. So what you will do? U is equal to integral. You will take from 0 to infinity, so that it includes all the frequencies that is available within the cavity. Then U nu d. So we will just rewrite it, because here you know the energy density, that is U nu d nu, that is equal to 8 by h by c cube nu cube d nu divided by e raised to h nu by kBt. H nu by kBt minus 1. So this is the expression, and this, if you take the integration of this is a kind of what is called a special integral, and this special integral has some special kind of what is called formula. So we will make use of it. We are not going to do it completely. We will just take the result. After doing this, you will get 8 pi raised to 5 k raised to 4 by 15 c cube, then this will be h cube raised to 4. So this is the result that you will get it after doing this integration. So this is actually this. It will be 0 to infinity. 8 x by c cube nu cube d nu divided by e raised to h nu by unity minus 1. So this you are going to integrate and you will get this one. So this here the only variable is t. Rest of the all are constants. Your pi, k, c, h all are constant. So you can just write it as this is equal to some constant times to 4. Okay. So this is the total energy density. This is total energy density U. Total energy density U. Now we can get the energy R radiated by an object per second per unit area. Okay. So this total energy is proportional to T raised to 4. So this the radiation energy per unit area per unit second, that will also proportional to T raised to 4. So we will write R is equal to the energy radiation. R is equal to R means this is the radiation energy or the energy radiated by an object per second per unit area. Okay. So this R is equal to E sigma e raised to 4, and this is called the Stefan-Boltzann law. Actually, these all need some kind of derivation, but these are all beyond the scope of our syllabus. I am just going to it. I just gave you how you got it. You are starting with your Planck's radiation formula, then you integrate it to get the total energy density. That you will get it like this. That is proportional to T raised to 4. If the total energy density is proportional to T raised to 4, that means the energy radiated by an object per second per unit area is also proportional to T raised to 4. Okay, so that is a simple concept, and that energy radiated is represented by the letter capital R, that is equal to E sigma T raised to 4, and here this E, this is called the emissivity, and sigma is called the Stefan-Boltzann constant. Okay, so this emissivity, that depends on the nature of radiating surface, and it takes the values from 0 to 1. Okay, so the 0 for a perfect reflecting object and 1 for a black body. Okay, so here I will write this is the Stefan-Boltzann law, and here this E, this is called the emissivity, and this emissivity, it depends upon the surface of the object. Okay, and it takes a value E is equal to 0 for a perfect reflected, and E is equal to 1 for a black body. So these are the values, and the Stefan-Boltzann constant or Stefan's constant sigma, here this sigma is called Stefan's constant. Okay, and this Stefan's constant sigma is equal to AC by 4, and it has the value sigma is equal to 5.674 into 10 to the power, sorry, 670 into 10 to the power minus 48 Weber per meter. Okay. So this is the unit. So the Stefan constant sigma is equal to AC.4, that is equal to 5.670 into 10 to the power minus 8, not plus 8, minus 8 Weber per meter square Kelvin raised to 4. Kelvin raised to 4. So this is the unit. And this is called the Stefan-Boltzann law. Okay, and this value of emissivity I told 0 for a perfect reflector. That means perfect reflector means which does not radiate at all. Perfect reflector means whatever it comes, it just reflects it. And E is equal to 1. It is for a black body that does not radiate at all. This is the minimum and maximum value. And in between you have different values for different materials. For example, if you are taking a steel, if you are taking a polished steel, for a polished steel is equal to 0. This is for a polished steel. And E is equal to 0.6. This is for a oxidized copper and brass, or oxidized copper and brass. Oxidized copper and brass. Okay. And E is equal to 0.92. This is for a black paint. So it depends. The emissivity, the value of emissivity, that depends upon the material in your hand. Now I will discuss 2-3 terminologies in the statistical mechanics, that is like statistical equilibrium, phase space, and also the entropy and probability, these relations. So actually this was in the beginning of your syllabus, but I am just completing your syllabus by discussing these things as well. Okay? So the statistical equilibrium. Actually, in thermodynamics we have studied so many equilibria like mechanical, chemical, thermal, and all these equilibriums in thermodynamics. So here the statistical equilibrium means that it is a state in which the probability distribution of a state remains constant over a time. So that means if you take the probability distribution for a long period, so if the probability distribution remaining same over a time, then we call it that state is called a statistical equilibrium state. So here you have to look at the probability distribution, and you just keep on checking the probability distribution over a time. If it remains constant, means this is a statistical equilibrium. So this may come as a short note or something like that. So you just when you prepare the note, you make the definition properly. And you can also say that this is a state of a closed statistical system in which the average value of the all physical quantities characterizing the state are independent of time. Okay, that means actually this basically your probability distribution remains constant. That is the essence of it. Okay, over a time. Okay, over a time. Then we put it as this is a statistical equilibrium. Okay, so I'll just repeat the definitions. One is a state. The definition first, there are different definitions. First definition you can say a state in which the probability distribution of a state remains constant over a time. And the second, we can also state in this way, this is a state of a closed statistical system in which the average value of all the physical quantities characterizing the state are independent of time. Then we call it as a statistical equilibrium. Okay, I will just write it here. You can take the definition from here. So these are the definitions. You can say a statistical equilibrium means it is a state in which the probability distribution of states remain constant over a time. Or you can also define it's a state of that is statistical equilibrium is a state of a closed statistical system in which the average value of all the physical quantities characterizing a state are independent of time. So these are the two definitions regarding the statistical equilibrium. So now we will go to the second thing, that is the phase space. So we will just discuss about a brief about the phase space. Generally, when you do our Newtonian mechanics, we take the things in configuration space. That means in the configuration space, your this Cartesian coordinate system, spherical polar coordinate system, cylindrical coordinate system, these are the different coordinate system that we are using. Okay. So here in the momentum space, so in the configuration space generally you have the position vectors x, y, and z in order to represent the position or a point in a configuration space. Okay. So some of the situations this is better to deal with the along with this what is called the coordinates, position coordinates. You can also take into consideration of the momentum, or generally you can say the what is called if Q1, Q2, Q3 are the position coordinates in the configuration space. So apart from this or along with this, you can also consider the Q1 dot, Q2 dot, Q3 dot. That means these are the velocity components. So in general, we make use of the position and the momentum. Okay? The momentum of this particle. So we will take the coordinates. That means if you have a system of n number of particles, then what we will do, you will have in this n number of particles, you will have Q1, Q2, Q3, etc. Qn number of our position coordinates. And along with this, you will have P1, P2, P3, etc. P and momentum coordinate system. You remember when you do the average energy of what is called an ideal gas using Maxwell-Boltzmann distribution function, we were using the momentum space where you have both the position and momentum coordinates. So in general, where you can move from 1, 2, 3, etc. up to n. That means each particle has 2D number of, if it is a 3-dimensional, 2D number of degrees of freedom. Okay, and your general coordinate for the n collection of particle you can write the general. If you generalize it, then the general coordinates will get you can simply write P comma Q, or this is nothing but P1 comma P2 comma etc. into P 3n. Then Q1 comma Q2 comma Q3. So this is a general coordinate in phase space. Okay. So more detailed about the phase space you will get it from your classical mechanics while you are studying the Lagrangians. Okay, Lagrangian mechanics. So for the time being, you understand phase space means here you have both the position coordinates as well as the momentum coordinates to represent a system or a particle in this space. Okay, so just imagine in this one it is little bit difficult because you have both the position and momentum coordinates. Okay. So for example, if you are looking for a 3-dimensional system, then you will have a total 6 degrees of freedom. If you are looking at a 3-dimensional system, then you will have, so in a 3-dimensional system, your Q and X, Y, Z, and P and R, X dot, Y dot, Z dot, the velocity component. Okay, of course, N, because here this n means for each particle you have this x. For first particle x1, y1, z1 and x1 dot, y1 dot, z1 dot. For the particle third, there is x3, y3, z3 and x3 dot, y3 dot, z3 dot, like that. So here the degrees of freedom is given by 2d. This much. Degrees of freedom. So that means for a 3-dimensional case, here d means what is called the dimension. So we will have in 3D, we have 6 degrees of freedom. So this is something about the phase space. You understand this, and the more details you will get it from your classical mechanics. Now, the last thing I would like to mention, that also just giving the relation of the relation connecting what is called the probability and entropy. The S, and if omega is the probability, the thermodynamic probability of a particular macro state, if it is represented by omega, then the relation between this is S is equal to K ln omega, where K is the Boltzmann constant, S is the entropy, and omega is the probability. Okay, the thermodynamic probability of a particular macro state. Okay, so this is the relation. This also you will study in detail from your MSc classes. So I just winding up with this module here. Okay, thank you.